know me, I think you all do. I'm Steve Gerber. I've been LRI for 3 years at Traverse City, and I've been a mentor for Team 1711 for 6 or 7 years now. So. Know a thing or two. I also work in the industry. I'm a project manager at Trantech Automation, where we design automated machines and robot mechanisms for industry. So I do this for a living. What I don't do for a living is teach kids how to do this for a living, so bear with me. I'm learning how to teach as you guys are learning some of this technical stuff. So. But what are simple machines? That's what we're going to talk about first. Simple machines. And then some of these other classes are going to concentrate on how we make machines work with some bearing technology, pneumatics, motors, reducers, and then we'll start talking about specific FRC topics down later dates with drive systems and electronic boards, that kind of thing. So, going back to my initial question, simple machines. Who knows what a simple machine is and how we define it? Anybody? Nobody? Okay. So, simple machine is basically a device that can amplify or de-amplify force. So when we talk about putting a certain force into an object to move it, a simple machine will take that force and either amplify it. So I can push down on a lever, for instance, and amplify a force by drawing a simple lever arm with a fulcrum. If I put a load down here and a load down here at equal distances, load 1 is going to equal load 2 at equilibrium point. But now if I turn this simple machine in and put the fulcrum point over here, now all of a sudden this guy has to work much harder to balance this guy. And that's a simple ratio of this distance here to this distance here. I've got a little video to show you to help illustrate that.
A famous ancient Greek once said, "Give me a place to stand and I shall move the earth." But this wasn't some wizard claiming to perform impossible feats. It was the mathematician Archimedes describing the fundamental principle behind the lever. The idea of a person moving such a huge mass on their own might sound like magic, but chances are you've seen it in your everyday life. One of the best examples is something you might recognize from a childhood playground: a teeter-totter or seesaw. Let's say you and a friend decide to hop on. If you both weigh about the same, you can totter back and forth pretty easily. But what happens if your friend weighs more? Suddenly, you're stuck up in the air. Fortunately, you probably know what to do. Just move back on the seesaw, and down you go. This may seem simple and intuitive, but what you're actually doing is using a lever to lift a weight that would otherwise be too heavy. This lever is one type of what we call simple machines, basic devices that reduce the amount of energy required for a task by cleverly applying the basic laws of physics. Let's take a look at how it works. Every lever consists of 3 main components: the effort arm, the resistance arm, and the fulcrum. In this case, your weight is the effort force, while your friend's weight provides the resistance force. What Archimedes learned was that there is an important relationship between the magnitudes of these forces and their distances from the fulcrum. The lever is balanced when the product of the effort force and the length of the effort arm equals the product of the resistance force and the length of the resistance arm. This relies on one of the basic laws of physics, which states that work measured in joules is equal to force applied over a distance. A lever can't reduce the amount of work needed to lift something, but it does give you a trade-off. Increase the distance, and you can apply less force. Rather than trying to lift an object directly, The lever makes the job easier by dispersing its weight across the entire length of the effort and resistance arms. So if your friend weighs twice as much as you, you'd need to sit twice as far from the center as him in order to lift him. By the same token, his little sister, whose weight is only a quarter of yours, could lift you by sitting 4 times as far as you. Seesaws may be fun, but the implications and possible uses of levers get much more impressive than that. With a big enough lever, you can lift some pretty heavy things. A person weighing 150 pounds, or 68 kilograms, could use a lever just 3.7 meters long to balance a smart car, or a 10-meter lever to lift a 2.5-ton stone block, like the ones used to build the pyramids. If you wanted to lift the Eiffel Tower, your lever would have to be a bit longer, about 40.6 kilometers. And what about Archimedes' famous boast? Sure, it's hypothetically possible. The Earth weighs 6 times 10 to the 24th power kilograms, and the Moon, that's about 384,400 kilometers away, would make a great fulcrum. So all you'd need to lift the Earth is a lever with a length of about a quadrillion light years, 1.5 billion times the distance to the Andromeda Galaxy, and of course a place to stand so you can use it. So for such a simple machine, the lever is capable of some pretty amazing things. And the basic elements of levers and other simple machines are found all around us in the various instruments and tools that we and even some other animals use to increase our chances of survival, or just make our lives easier. After all, it's the mathematical principles behind these devices that make the world go round.
Alright, so you guys have any questions from that? No? Do you think Archimedes could move the Earth?
Well,
Well-
you gave him the right place to stand.
Okay. But what force does Archimedes have to move the lever? Gravity. Where is he getting the gravity from? Earth.
The problem is there isn't gravity, so it wouldn't work like that.
You're right.
But if you, in theory, if there's a flat or a giant, even more massive body that could replicate the same gravity of Earth, but across the quadrillion light year span, could do it.
Sure.
Without Earth flattening into that.
He was closer to another celestial body that had some weight on another planet. He could have done that, right? So the point is that the simple machine can amplify a person's weight, 150 pounds in this case, to move just about anything with the right lever. Now, we can apply that to robotics in a lot of different ways, but mostly we do that not only through levers, but also through some of the other simple machines as represented in that movie. The negatives, something we're not going to talk a lot about tonight, but some of the negatives of machines are the efficiency or losses to friction. So that needs to be addressed, and it's more of a complex subject, so we're not going to touch a lot on it tonight. But basically, when we get into the wheel and the axle or gearing ratios, there are some losses associated with those types of simple machines, and those we relate to as an efficiency number. So if we talk about a spur gear, it might be a 95% efficient spur gear, meaning if you put in 100 pounds to the inside of your force applied, you're only going to get 95 pounds out, and that's due losses to efficiency. So just keep that in mind as you go through your systems and you design them. There are some losses associated with some simple machines. So getting back to the lever then, there are several different kinds of levers out there, and one in particular, I'm just going to pull an example that we used this year on a Raptor's machine, was a Class 2 lever, in which case one load was out here, and we wanted to push up here. We had an arm that had a pivot point back here. that was load 2, so this is load 1. So distance 1 in this case is the distance from the fulcrum to the force, and then distance 2 is from the fulcrum to the load. So the same equations apply. L1 times D1 are going to equal L2 times D2 at an equilibrium. And we ran through this calculation to make sure that we had enough force applied at this point here to move what we assume to be the load at this lever arm here. So there's all kinds of variations to these levers that you could take and apply to mechanism design. But that's one we used this year right there. We had to size that pneumatic cylinder to lift the loads that we expected out here. Any questions on that? Okay. There's also what they call a class 3 lever. It's just essentially the second class lever, only the load and the force are reversed in that situation. So in that case, class 3 lever is the load, this essentially being force, or load 1 here and load 2 here, so it's just a variation on this class 2 lever. No other questions? Let me shut this off. Now, when we talk about the next simple machine, we're going to talk about a wheel and an axle. And this one applies to robotics quite easily. Basically, you have a wheel and an axle with a loading up here, and then they have a smaller wheel in here with your force too. Let's say load 2 here. So basically, you have 2 different size wheels running on the same axle. Anybody think of what this looks like to them? Go ahead. You say.
You have a wheel and then you have a belt running the wheel? Or would that?
Could be, but there's a better application. Ready, Zachary?
A gear system?
A gear system, perfect. So you've got a spur gear inside your, if you ever torn a gearbox apart, you've got spur gears, right? So you've got an axle, and you've got a toothed gear here, and a toothed gear out here, okay? The ratio between this radius right here, I'm gonna call this R2, and then this ratio right here, the radius, this is R1. So here again, this is your distance, and this is your load. So this is basically a modified lever, only it's in a continuous rotating fashion. So you take and apply that simple lever system to here. So in this case, again, L1 times R1 is going to equal L2 times R2. And you can either measure in a tooth system, you can either measure the radius, or you can just count the teeth. This would be like a 10-tooth pulley, and this may be a 30-tooth pulley, in which case, if you boil this down, your mechanical advantage is 3-to-1 with this system. So you put your 30-tooth over your 10-tooth to get a mechanical advantage out of that. Mechanical advantage is how we classify the simple machine, as far as how good it is, or the ratio of the machine going in. Your mechanical advantage, it would be R1 over R2, or in this case, would be 3-to-1. You can do that same thing for the lever. You can also do that same thing for our next machine, which is a simple pulley system. And I brought in an example of a simple pulley system. So this is another simple machine here. I'm going to turn this around that way. In a pulley system, anybody ever use a block and tackle here? No? Okay. So in a pulley system, you put your load here. So I'll erase this guy. So this is your load. This is your advantage of this one is a simple machine, is simply the number of ropes between these two pulley points. So in this case, it's
Just one, or is it two?
It's two. So if we draw a line between these two
Oh,
axles,
yeah.
right here, you've got 1, 2. So it's a 2-to-1 machine, or a mechanical advantage of 2. So if I put 50 pounds here, how much force do I have to pull here?
25.
25, plus any frictional losses within the system. The disadvantage for something like this is, if you notice, let's say these are equal distance here, if I want this to move 1 feet, I've got to pull this thing
2 feet.
2 feet. And that's where the trade-off comes. You can't make energy from a simple machine. You're trading off how much force is needed for how much distance is traveled. But in many cases, because you're using motors and actuators, you can make up for that distance in whatever mechanism you design, either with a belt or a chain or whatever. Any questions on the pulley? No? Anybody ever use a pulley system in the robot?
I've used a few pulley systems.
Where have you used it?
When I was in elementary school in 5th grade, we had this big Rube Goldberg project,
Okay.
and mine revolved around a lot of pulleys and gears and such.
Okay.
So I had to use it to pick up, I'm not sure what the end result was, but I think I picked up something relatively heavy, like a small brick or something.
With a lesser force.
Yeah. Yeah, it started with the push of a domino, which is
Nice.
classic.
Okay. So you can also get obviously more pulleys and more ropes, and then that mechanical advantage is always the number of ropes in between the two kind of pulley systems. Our next simple machine that we're going to talk about is the inclined plane, which is basically a sloping weight block, if you would. So if you've got a weight, let's load 1, and you want to move it this distance, let's just call that 4. You can either lift that up, those 4 units, or you can take that weight and slide it up this distance here. Which one requires more pushing, or more load, more force?
Pulling it up, directly up.
Yes, it does. Pushing this way, let's call this L2. L2 is a lot less than L1, and we can represent that by the distance that it has to travel. Essentially, this is, I'm just going to guess, this is 8 here. Then the distance of this over this is our mechanical advantage. Any questions? I don't see that used a lot in robots. Occasionally for a stopping mechanism or something, you'll use a wedge, but that is a valid, simple machine. The next simple machine is kind of a variation on that, in that you take and have a wedge shape, like that. So if you're driving that wedge into a tree or some other variation of wanting to split apart something, there again. Your mechanical advantage is still this distance here or that distance there. So simple machines are all about mechanical advantage. How much can you gain in the system to make your motor work, or to make that mechanism that wants to push-pull work? Or sometimes, if you've only got a short actuator, you need to use a simple machine in the other way. You want to move a long distance and you've only got a short actuator, put the short actuator on a small lever arm, it doesn't have to actuate as far to move that load a big distance. You just need a bigger actuator. Does that make sense? Okay. All right. The last simple machine that we got out there is what they call a screw. That comes in many different flavors. Some of which you've probably seen, some of which you probably have not seen. I don't know how many of you have ever seen a ball screw actuator? No? All right. Well, that is somewhat complex, but I'm just going to draw a simple screw here. Threads on my screw. So the mechanical advantage of screw, basically if you look at a screw pitch, you've got a P, or a pitch to the thread screw. You imagine if the distance between the threads, that's your pitch on your screws, right? So the finer this pitch, the more your mechanical advantage. So mechanical advantage is 2 pi and L, I'll define L here in a minute, over B. L in this case is the lever arm put in there to turn the screw. Imagine this lever turning this screw about some circumference here. The pitch of that screw being here, your mechanical advantage for that system is 2 times pi times this distance divided by your pitch. So the smaller and smaller you make this pitch, the bigger and bigger your advantage is.
So the idea is that the finer, like the pitch is, the less force it takes to screw it in, but the longer amount of time you have, or the longer distance, I guess, you have to rotate it down? Or
If I understand what you're asking, if I have a 1/4-20 pitch here, I'll have to turn that 4 times to go, well, just turn it 1/4-20, 20 times to go an inch. If I've got a 1/4-28 pitch here, I got to turn it 28 times to go in. But the 1/4-28 is actually a higher mechanical advantage. So I would need less force here to turn it, but I'd have to turn it more times.
Yeah, that's what I was.
Okay, yeah, that's a true statement. So a lot of times you'll see screws in, I think I mentioned this before, a ball screw actuator. So basically what they do is they'll take a thread and a piece of rod, and there's acme threads, and there's all kinds of different threads, and they'll put a nut on that. Okay? And inside that nut, they have these recirculating balls. And those balls go around like this, so they travel inside the nut, actually. We got balls on this side, too. So these balls are going around. While a motor is turning this, that nut will travel back and forth like that. So that's a ball screw actuator. You can get nuts like an acme thread that is basically a really large pitch screw with a bronze nut on it. And that does the same thing. They just with the sliding friction versus this is what they call whirling friction. Given the bearing discussion, we'll talk about that in a little more depth. But basically, your efficiency of this simple system is a lot better with the rolling actuator than it is with the sliding actuator. So the ball screw nut is a much more efficient system.
And that's just used to like screw something down.
It basically takes a rotary input and translates it to a linear travel.
Okay.
So your mechanism, if you want, your mechanism would attach here to the outside of this nut, and then this guy goes this way and goes this way, right? And the motor sits here, and it's probably on a reducer. It travels this way and this way. So if you wanted to raise an elevator, for instance, you turn this up, you could raise the elevator with one screw. Or any other kind of linear travel. You could actually, they make electric actuators out of this a lot of times. So you've seen your pneumatic actuators. You can also get an electric version of a pneumatic actuator. And they put this, you know, this then becomes this, like a cylinder looking thing, okay? And they have, you know, attachment points here, and then this whole thing travels like a cylinder does up and down that pipe. So it's called an electrical actuator. And that's the basics behind a lot of the conversion from pneumatics to electrics. They'll use a ball screw and a reducer. Any questions in the back? Girls are pretty quiet. No? Learn anything?
Yes.
Good. All right. Any other questions on how we might apply these simple systems to a robot? I mean, these basic 6 simple systems are what make 99% of your robot moves. Your drivetrain is simply a spur gear. Those simple boxes in there, they're spur gears. They're a wheel and a wheel. You put lots of them together to make a complex system, but they're simple systems all put together. Your actuators, your lifts, they're probably either levers or something like this. All these seem really simple, and it really is, but they just combine these actuators into mechanisms that control actuation on the robot. Mark, you have any questions?
Could you perhaps maybe talk about which one has more force? Because we haven't gotten into like the material properties of the classes of lever when you're trying to lift stuff versus when you're trying to lift stuff with something like that.
Well, your forces really play in the sizes of your actuators. They're not the simple machines don't really apply themselves to more force or less force, except for the efficiencies between them and the different mechanical advantages that you utilize. I've seen a lot of levers lift very large forces, and conversely, the ball screws are good for that as well. A lot of times you'll find ball screws on levers. I mean, it just depends on individual mechanism design as far as which one's more suited for which forces. So I guess my answer to that would be it just depends on the mechanism design. What you've got room for, whether you're trying to increase the travel or decrease the travel. I'd say it applies probably more to the type of actuator that you're using. I think I see levers more often associated with pneumatics than most other things. Probably because pneumatics have a defined stroke. Whereas if you're using a motor-driven system, obviously your motor goes, there's no limit to the number of revs you can put in a motor. For instance, your drive system. You're not going to use a lever in a drive system because you've got a limited travel in your lever system. So you're going to use a spur gear system on the drive. Conversely, if you've got a limited motion to the actuator, your lever or your ball screw would be more suited for those types of things where you've got a limited space to move, where you want to move a certain distance.
Definitely packaging is always.
It's always key in robot design, for sure.
And then this year, a number of robots had a mechanism like that just to lift their robot up.
Yes, true statement. True statement. Well, that's the limit of what I had to talk to you tonight, guys. I hope you learned something from it. I hope you can take this and apply it to your next robot design. That's all. So I'm here for questions. Thanks for coming.